All right, example 2. Use the comparison test to decide whether each of the following integrals converges or diverges. If an integral converges, find an upper bound for its value. So for this first integral, as soon as I see that e to the x in the denominator, I'm thinking back to this reference integral. And if I can compare it to this, that's probably going to help me. And again, I need to have kind of an idea of whether I think my integral is going to converge or diverge. Now, knowing that this is the reference and this one converges, I would like to believe that this one's going to converge also. However, we can take a look at the graph. Here's the graph, and as x goes from 0 to infinity, I kind of observe what's happening here. It does seem like the shaded area is probably converging. So I'm going to begin with that assumption and see if that works out. So once again, I'm going to begin by thinking, okay, this one seems to converge. Is it non-negative? Well, again, if you plug in positive values into this denominator, yes, it's going to stay positive. So this is a non-negative integrand, which means we can use the comparison test. And if we think we want to prove something converges, we are looking to find an integrand to compare it to that's going to be bigger. All right, so to begin with this one, again, I want to just kind of isolate the denominator and think about what I can compare that to. So I'm looking at e to the x plus x, and I'd like it to compare it to just plain e to the x. So what's the relationship there? Well, obviously, if you just have the base function on one side and on the other side you're adding a positive number to it, then we know that this left side will be bigger than the right. As we did in the last one, we're now going to look at what happens when those become the denominators of fractions. If you compare these two fractions now, the one on the left is going to have a bigger denominator, so we're dividing by a bigger number, which will cause that overall fraction to be smaller. So at this point, I've shown that this function is bigger than the one that I wanted to compare it to. So again, that's good news if I'm trying to show convergence. Now, all I have to do at this point is say that we know 0 to infinity, 1 over e to the x dx converges to 1. And I can say that automatically because, again, that's one of my reference integrals, so I don't have to go through the whole integration process. And since this integral converges to 1, and the integral that I am interested in is smaller than that integral, or again, saying it the other way, that my comparison integral is bigger than the one that I'm trying to show convergence for, I know my integral has to converge. And finally, for the integral that converges, we find an upper bound. Again, it's going to be something smaller than 1 because our comparison integral was 1. And again, the comparison test at the very end here says that your integral will be less than or equal to the one you compared it with. And so I guess I could continue here, must also converge to a value less than or equal to 1. All right, let's take a look at another one. All right, now this integral right away, what kind of jumps out at me is the 100 that's sitting down here. That seems odd. You know, we like our lower limits to be zeros or ones for this, so I'm going to have to figure out how to handle that. It's improper because it has an infinity. And we're looking at 1 over the square root of x. So again, converge or diverge? Here's the graph of 1 over the square root of x. And if we're looking at the area under the curve, we're specifically supposed to look from 100 to infinity. So I'm going to change my scale. I've adjusted my scale so I can see starting at 100. And again, my function is still declining. And the question is it going to do this infinitely? Or will it eventually stop and converge and take on a finite value? It's kind of hard to say from the graph. So this time I'm going to dive in saying I'm not sure what this integral is doing. I do know it's going to be non-negative because I'm plugging in values from 100 to infinity into the denominator here. So I do know it's non-negative. And I do know then that I can do a comparison test. All I'm going to do is I'm going to start by taking a look at my denominator. I'm going to look at my denominator thinking of it as square root of x, and I want to compare it to something simpler. So wouldn't it be easier if it was just x instead of square root of x? All right, now what's the relationship? The square root of x is going to be bigger than or equal to x, correct? Now think of putting those on as denominators of fractions. And again, what's going to happen is because the bigger denominator is on the right, that's actually going to be the smaller function. So what I see here is the fact that the integrand that I'm interested in is actually the bigger one. And the one I'm comparing it to seems to be smaller. So that should suggest that this one is going to diverge. But we still have some work to do here. Next, I'm going to work on these limits of integration. Bear in mind that the square root of x is really x to the 1/2 power. And when we think of powers of x in the denominator, you've got a nice reference integral. The p-value that we have is a fraction 1/2, which is less than or equal to 1. So I know the integral from 1 to infinity is going to diverge. How does that help? Well, I want to have this be my integral because I know what to do with that one. Think about the shaded area. The area from 1 that accumulates all the way to infinity is going to be bigger for sure than the area starting out at 100. So this integral is too big compared to my original. I'm going to subtract off that extra area from 1 to 100. And based on the properties of integrals, you should be familiar with the fact that if you have the integral 1 to infinity and you take off that portion from 1 to 100, you're left with the portion from 100 to infinity. Since we've already shown that our integrand is bigger than our comparison function, or again, saying it the other way, the comparison function is smaller than our integrand, we know that this right-hand side diverges. In particular, we get this one directly from the reference integral, where the power of x is p equals 1/2. Anytime your value of p is less than or equal to 1, your integrand is going to diverge. The other integral is a proper integral and therefore will be finite, and subtracting a finite amount means this is still going to diverge. So you can see how you don't really have to be certain what's going on in the beginning to still take steps forward and see where comparison test will take you. All right, now the last integral that we're going to take a look at here, it's improper, 1 to infinity. Does it converge or diverge? And my function this time is sine of x over x squared. Let's go take a look at what that looks like on the graph. Now, at first glance, this one looks again like another one of these that's kind of just curving toward the x-axis. But if you observe closely what's going on here, remember that there's a sine function in here, and that sine functions are periodic. So I'm going to adjust to a more appropriate trigonometric scale. All right, so you can see I've gotten some nice radian values here as labels for my x-axis. And observe the behavior of this function. Notice once it hits pi, it drops below the x-axis, then it goes back above, then it goes back below. And that causes us a problem in terms of being able to apply the comparison test at all. We just observed the fact that sine of x over x squared takes on negative values. And because of that, we can't use the comparison test. So always keep that in the back of your mind that you really do need to look at your function first and decide if it's appropriate to use comparison test in the first place. The other integral is a proper integral, and